Okay, we have the set here. It's orthogonal to the vectors. So we just got to show that the scalars. This set is also orthogonal with the scalars. Just we know this is orthogonal, we know it's linearly independent, so therefore they equal 0. So we have u1 in the I hat direction and then uj in the u in the j hat direction. We just evaluated it at k1 u1. We put in component forms, take out the k values, we get this is this, 0, they're all both 0 values here. Therefore, any k values there times 0 will be 0, therefore it's orthogonal. Here we use Gram-Schmidt's algorithm application to project vectors onto one another, essentially. So we have v1, v2, v3. We equal u1 equal to v1. u1 equals v1 over the length of v1, which is just following Gram-Schmidt's application here. And then this is the projection equations that we'll use to find the u values, but these are, I wrote them as primes, as one of the videos did as well, in order so we can find our actual u2 values and u3 values here. So u1 equals here 1/2 times pretty much the vector 1. I wrote it in matrix form this way, equals this. There we go. U prime 2, following the projection equation here for Gram-Schmidt's. Do all the math, and then we end up getting with u2 equal to 0, -2, 1, 1 matrix here. Find the length, times it by that. We get this right here, square root of 6, 4, 1, 1, 6. And then u3, the projection on to it. Follow the equation, we get this matrix here. Find the length so we can pretty much divide it by it. We get this right here. Therefore, our values here are this right here. v1 times v2 0, v1 times v3 0, v2 times v3 is 0. Basically, Gram-Schmidt's equation. Here we have this. I just went ahead and did that really fast. And basically our orthogonal basis of the view of v1, v2, and v3 is this. Same deal here, projections and our u1, u2, u3. I decided to make u1 and u2 of just basis w, based on the question asking for it. And then we project w onto v, follow the equations here written out, we end up with getting the projection of w onto v, which is equal to this side right there. Essentially the same thing, but the other way around. v1 equals u1, to find u2. This is the same as part A, so I just took that, solve for u2. Went ahead and add them, and we get this. Same deal, just following the math equations. Here we have to determine the matrices are positive definite. I wrote it wrong here, but basically what I chose to do is if it's symmetric, I'll find the pivot points and ensure that the pivot point of that A of the row column thingy of the essentially matrix, I believe, is greater than 0 for any value equal to 1 or greater than 1, and pretty much infinity to the positive side. So what we do is we evaluate it in chunks here, the pivot points. A1, this right here is 1, A2. Essentially, we're just going to do the Workstein's, whatever you want to call it. I just call it the cross product because it just makes more sense that way. Just do the cross product. 5 minus 9 is -4. Both of these are not positive because this one's negative, so therefore it's not positive definite. Same deal here, symmetric 2 by 2, 2 by 2, 2 by 2. Again, 1, 3. Cross product, get a positive value, it's 5, greater than 0, positive. Right here, 4, 1. 4. That's A1 greater than that, and then value A2. Cross product 4 times 1 times 2, 0. I meant to change this to not positive definitive because it has to be greater or equal to 1. It cannot be 0, so this is not positive definitive. I forgot to change that. Here, same thing, 3 by 3 symmetric, A at 1, 2, A at A2, which is this chunk right here, cross product, 2 valuable. And then this pivot point here, A of 3, do the cross product or worksheetians, whatever you want to call it. 1 equals 1 is greater than 0, so it's positive definitive. Same deal here, except this is negative, so we get the answer to not be positive definitive because it's less than 0. Okay, here we have matrix A plus B. We know based on the formula theorem that x transverse of A times x is always positive for all the vectors of x that do not equal 0, so therefore we know that this has to be greater than 0 when the x values don't equal 0. So essentially we're just going to plug in A, B, do the math. Here we get this. We know that x transverse of A to the x is in positive. The same will be for B. Therefore, this whole equation is greater than 0 because none of them are pretty much 0 values. So A plus B is a positive definitive. Same deal here with k times A. We're noted that k is greater than 0. Vectors do not equal 0. Plug it in. Same deal. None of these are 0 values. Therefore, it's positive. Positive definitive. And then here, find the symmetric orthogonal matrix of P for the first row. I decided to follow the theorem of this right here. So we need to find our order basis for P of 3, which is the set. We find our W1, W2, that's what just decided to label it. It's our determinants here. And then V1 equals V1 following basically Gram-Schmidt's equation again. Application of, so V1 equals W1, V2 right here, follow it out, same deal as before. Here's V3, follow it out, we end up getting this right here through all that math. So now we have found our orthogonal basis, which needs to be normalized. And that's their U1, V1, U2, same thing, divided by, basically, U1 equals V1 divided by the length of it. Same for U2 and U3. Go ahead and did it. And then that will give us our orthonormal basis for this whole question, which is right here. That